Let's talk about the Aldol reaction. Now, before we get into any examples or even the mechanism, let's just look at the overall effect of the reaction. So basically, the Aldol reaction is a method of forming carbon-carbon bonds between two different or two of the same carbonyl compounds. We're going to harness that alpha acidity as the nucleophile and use the carbonyl electrophilicity as the electrophile. So we hook them up together in that kind of behavior. So here's the overall effect. Let's start out with a general carbonyl. It could be an aldehyde or a ketone. And with this, let's bring in another one. So this first step in the Aldol reaction involves forming the enolate on any one of these two. For simplicity's sake, let's call this compound the nucleophile, the enolate, and this compound the electrophile. So let's say we just isolate this carbonyl and we form the enolate only here. And we just isolate it from this carbonyl compound. Let's just use some generic base. Now in the second step, let's add the electrophile and keep it in this basic and aqueous environment where we do have proton source in the form of water. So what happens is we form the aldol, which looks like this. So now the aldol is also called the addition product, which is also a beta hydroxy aldehyde or ketone. Because 2 carbons away from the carbonyl that is a part of the nucleophile, the enolate, we have a hydroxyl group. And we know the alpha carbon as a part of the enolate is the nucleophilic portion of it, which is shown right here. I guess to make it more accurate, let's add another carbon, like that. Now again, this is a very generalized way of doing it. There's a lot of caveats. For one, we can form the enolate at R2, theoretically. There's no control. On top of that, this could also function as an enolate, depending. But what we're trying to say is that this compound functions as the enolate. On top of that, we're only focusing on this alpha carbon, which is next to R1 and not R2. So given these conditions, this is the outcome, the beta hydroxy carbonyl. And the carbon-carbon bond that is formed is between alpha and beta. So if this is the alpha nucleophile, that means the carbonyl carbon, which is electrophilic, is beta, which means alpha attacks beta. The nucleophile attacks the electrophile. And with an aqueous workup, we form what's called the addition product. Now we can take this one step further because this intermediate isn't necessarily stable. We can expose this reaction to acid or base, and more importantly in the presence of heat, which gives us the aldol condensation product, which looks like this. Importantly, the double bond forms between alpha and beta carbons, so that is where we see the pi bond. That's why the condensation product is also called the alpha-beta unsaturated carbonyl. And usually it's because you're exposing the compound to heat. But overall, this is the effect of the reaction. And it's really versatile, because if you take this substrate here, kind of complicated looking, and this, we understand that this is a non-enolizable compound. There is no alpha carbon, which can be readily deprotonated to form the enolate. In this case, this modified acetophenone is the only option. So we classify this carbon as alpha. It's a primary carbon, so it's fairly acidic. And on top of that, we have an electrophilic carbon here. So we just hook up alpha and beta in the presence of base and heat to form this compound. So a very versatile synthetic tool to form carbon-carbon bonds. In this example, again, we have a non-enolizable compound. Benzaldehyde doesn't have any alpha hydrogen, but it does have an electrophilic moiety. So with acetone, we have acidic protons on these alpha carbons here, which upon deprotonation will attack beta. The nucleophile attacks the electrophile. And with some exposure to heat, we get this compound. And it turns out we also have an alpha here, which hasn't reacted. So that can be deprotonated, and that can attack another benzaldehyde to form this final product here, which is crystallized. Now, for the aldol reaction to undergo full condensation to form the alpha-beta unsaturated carbonyl, we need 2 alpha protons. If only one is present, the addition product only forms. And later we'll see why we need this additional alpha proton. So now let's look at the mechanism. We'll use acetophenone and propanol. And theoretically, if you're not controlling which compound is the enolate and which one is the electrophile, theoretically any one of these 2 compounds can function as a nucleophile. In propanol, we have an alpha carbon, with 2 acidic protons, and here, perhaps even more acidic, we have 3 acidic protons. So if propanol is functioning as the nucleophile, that means acetophenone is the electrophile. So what happens is we form this compound. But if acetophenone is the nucleophile and propanol is the recipient, the electrophile, we form this compound. So there are 2 pathways that we see. What isn't shown here is that propanol can react with itself, and so can acetophenone. But for simplicity's sake, let's focus on forming this compound, and let's focus on the mechanism for this, using propanol as the nucleophile. So step 1 is critical. To form the enolate, we need at least 1 alpha proton. In this case, propanol has 2. So using sodium hydroxide means, as a Lewis base, it can pluck off this alpha proton, relatively acidic. The electrons travel back into the compound, typical arrow pushing. So we form this intermediate, resonance form 1, which has an alkene between the former carbonyl carbon and alpha. Now the negative charge can be dispersed, and we see that if the carbonyl is regenerated and these pi electrons are concentrated back to alpha. So we get resonance form 2. Now it turns out the nucleophilicity of this negatively charged oxygen is attenuated, and that's because of these counter ions which come with bases. So sodium hydroxide has sodium as the positively charged ion in solution. As the cation, it can complex with this negatively charged oxygen, and it turns out this is the more stable resonance form. So really, this oxygen isn't as nucleophilic and therefore requires stronger electrophiles to harness its nucleophilicity. So again, for simplicity, we focus on alpha nucleophilicity. So that's the second step. We've already formed our enolate, and then we slowly add in acetophenone to the solution. So propanol at the alpha position will attack the partially positive carbonyl in acetophenone. The carbonyl oxygen can bear the negative charge, and we form this intermediate here. Now what's the trick to stitch together the nucleophile, the enolate, and the electrophile, the carbonyl? Now the first method is to number all of the carbons, which is the first approach you should use. So what we do is we start numbering from here. Let's call this carbon 1. We continue all the way up to the nucleophilic carbon, carbon 2, and we stop there. We know that 2 is nucleophilic and will attack this carbonyl because it's electrophilic. Let's call that 3. And then finally, we terminate here, that's 4. So this is a pretty systematic way because then we can just draw butane and expand it from there. So let's draw butane and analyze all of the carbons. So carbon 2 importantly bears this aldehyde group. So we can draw that as an extension. Let's call it 2 prime. Now 2 is attached to 3 and we see that. 3 has 2 important groups coming off of it. We have the phenyl and the methyl group. We see the methyl group is already attached at carbon 4. So let's bring in the phenyl group right here. And also, because of the attack, the oxygen bears a negative charge, which is waiting to be protonated. So let's draw that alkoxide oxygen right here, okay? This is called the addition product, where at the beta position, we have the precursor to a hydroxy group. This is one method. Now, as you practice this method and get more used to it, there are some tricks to really speed this up. All we need to do is recognize alpha and beta. We know alpha's here, and we know the nucleophilic carbon in this carbonyl will attack the electrophilic on this one, like so. It turns out alpha is attacking beta, the carbonyl carbon, which is electrophilic on rather the receiving party, right? The receiving carbonyl, or the non-enolizable carbonyl, is always beta. The shortcut then is to look at the nucleophile, in this case an aldehyde, and draw that first. And we must label alpha so we don't get lost. We know alpha is bearing some group, in this case methyl, but it could be anything. So let's just flip that group down and draw it like this. We know alpha is bound to beta. And just like we discussed, the addition product is the beta hydroxy carbonyl. So instead of the hydroxy, we have that precursor, the alkoxide. So let's put that in. At beta, we have the 2 variable groups. We have the phenyl and methyl. So let's add that in. Here's the phenyl, and here's the methyl.